Hello everyone and welcome to Calculus. Today we're going to be finding the volume of a region using washers. So last time we did this we used disks, so these problems are just a little bit more complicated, but you're smart, you can do it. There is a formula, but I'm going to jump straight into the example and then come back to the formula because I think that that'll be the easiest way for you to understand how the formula works. So let's start by making our graph. That's always the first step. I have y is equal to the square root of x, 0, 0, 1, 1, 4, 2, looks like that. And then I have y is equal to x squared, which is the inverse function, 0, 0, 1, 1, 2, 4, and it looks like that. We're going to revolve this region around the x-axis. So here's my region right here. And I'm going to revolve it around the x-axis. So now I'm going to flip my blue one. It probably is easier if you flip them independent of each other instead of just trying to draw the whole thing. And then 0, 0, 1, 1, 4, 2, so like that. So this is a little bit complicated to see, so I'm going to kind of blow it up here. We have something that from the outside, when this outer curve comes around, it flips over this line. You actually can't see that interior at all. This is all you would see from the red graph. But then if you could walk over here and look from this direction inside it, you would see that it was missing a section. It had a cutout that was symmetric around that line. So when it spins around, all you see is this outer shape. But if you could walk around to the side here and look in, that's when you would realize that there was a piece missing. So what does that mean for our disks? Well, since this entire piece is missing, this first disk, if we were to run it through our slicer, is actually just a washer. It's just like a ring. It has no inside at all. But then when I get to this slice on my slicer, so if you didn't watch the other video, we're running it through a deli slicer so we can see what lands. And the first one would just be a ring. But right here, this one would be what we call a washer. It would like a donut. So it would have the outer section, but then it would have a little piece of it cut out. And then when we did this slice, when we got to that part of our solid, we ran that through the slicer, it would be smaller overall than the original, but also this little ring inside would be smaller. And eventually you would hardly be able to see the little ring, and eventually it would just be a dot. And if you put all those washers stacked up, you could get the original volume. So we want to stack up all of these washers. We're going to stack them up. We're going to add their areas. So what is the area of any one of these? What is the area of this shaded region? The first one, remember, was just a ring, so it didn't really have an area, just a circumference. So I want to add all those up. If you were in 5th grade and I asked you to figure this out, hopefully you would say, well, it's the outer ring, pi r squared, whatever this big radius is there, minus the area of the little circle, which would be pi, let's call that little radius, r squared. And that's where we get this formula that you see at the top. The volume is going to be pi. They factored the pi out, but pi capital R squared, that's because there's a big ring. So from there to there is R, and then there's a little ring. From there to there is R. So it's area, if you move that pi back in, area of the large circle minus the area of the inner circle. That's what would give you the shaded area. So once you understand that concept, these problems are a piece of cake. Which one is making my outer ring, the red or the blue? It's definitely the red. So pi r squared minus, and then the inner ring is being made by the blue one, pi r squared. So just like last time, I highly recommend that you write the setup first and then think about the diameter. So the diameter of the outer ring is created by the red, so it's just the square root of x, but this way I don't forget my square. And the inner ring is created by the x squared. So this is a easy enough integral to do, but it's easier if you take that pi out, and then this is just going to be the square root of x squared is just x minus x to the fourth. We'll write our dx in, which technically means it needs some big parentheses. So that is pi times x squared over 2 minus x to the fifth over 5 from, so where is this slicer going from? From 0, and I start slicing until I get to 1, 0 to 1. And when I plug that in, I get pi times 1/2 minus 1/5 minus pi times 0. Always plug that 0 in. Most of the times it's 0, but when it's not, you'll get caught on that. So we have 5/10 minus 2/10, which is equal to 3/10 pi. Let's try another one of those. Find the volume of the solid generated by revolving the region bounded by the curves y is equal to x squared again, and y is equal to 2 minus x squared, about the x-axis. So you don't need to make this really big, because we know that this one's going down. It starts at 2, but then it's going to be going down. So 1, 1, and then 2, 1, 2, 3, 4. So there's my 2 minus x squared parabola. Doesn't have to be a perfect sketch. Just want to see the basic shape of it. And y is equal to x squared. 0, 0, 1, 1, 2, 4 would be somewhere up there. It looks like that. Actually, I do want to pass through that point. There we go. Okay, so if we were just doing the area between the two curves, it would look like this. But we're gonna revolve this weird shape around the x-axis. So people's biggest problem with this is definitely visualizing the shape. So my recommendation is that you flip each one of them independent of the other. So this goes up to 2, so let's go down to 2, and then we got our 1, 1, and we're going to draw it like this. That one's been flipped, and now 0, 0, and I got my 1, 1s. Now that one's been flipped. And if you want, you can even erase anything that's extra if it's going to make it easier for you to think of just this shape being flipped. Okay, so what does it look like to flip it? So this point is going to come around, and then this point is going to come around, and then this point is going to come around. So when that happens, what do you see? I see this top shape coming around like this, and then it's flat because it doesn't come around all the way until it reaches the axis like that. It suddenly stops. Really hard to visualize. So you've got this, I'll make it a little bit more pronounced. Got this shape, and then it suddenly stops. And if you were to see this coming at you, you would see this coming around. But if you could walk over here and look inside of it, you would see, not all the way through, but you would see this cutout. Or if you were to walk over and look at it from this side, you would see this cutout. But only if you walked over. If you were standing here, then this would be rotating straight at you. It would be like an egg, but because it cuts off all of a sudden like that, this piece right here would be very, very flat. So the cross sections, when we run it through our deli slicer, I'm going to run it through my slicer, and when I get to there, I have a very distinct washer. So a washer area is easy to find. It's the area of the big circle minus the area of the little circle. That'll give you the actual area that you want to add up. I want to add up all of the washers, even though this one is pretty much just going to be a ring and this one's going to be pretty much solid. I want to add up all of the washers from, where am I going to start my slicer? I'm going to start my slicer over here at -1, and I'm going to keep slicing until I get to +1. Or you may want to start at 0 and go to 1. Do you know what I'm going to do? Multiply by 2, because they're symmetric, so it's the same on both sides. And in addition to that, I think I'm going to make room there and take out my pi. So 2 pi, and then capital R squared minus lowercase r squared. And what does that big radius come from? What makes that? The higher one, the red one, the 2 minus x squared. And then what does the little one come from? The x squared. So I'm going to put some brackets around that so I can put my dx in. And before I actually integrate, I am going to simplify. So this is 4 minus 4x squared plus x to the 4th minus x to the 4th. Ooh, that worked out nice. So those cancel. And now my actual integral will be 4x over 1 minus 4/3 x to the 3rd from, remember we're going from 0 to 1. And when I plug in a 1, I get 4 minus 4/3. When I plug in a 0, I get 0. So nothing to worry about there. I do need a common denominator. So 4 is the same as 12/3 minus 4/3 is 8/3 times 2 is 16 pi/3, which is our answer. Great. Let's try another one. Actually, if you're ready to try one on your own, the answer to number 3 is pi/3. The answer to number 4 is 3 pi/2. And the answer to the last one is pi/2. So if you have any interest in doing those on your own, those are the 3 answers. But of course, I'm going to do them for you. Find the volume of the solid formed by revolving the region bounded by the square root of 1 minus x squared and 1 minus x around the x-axis. So again, I'm hoping that you've started to recognize this. This is a half circle. Y squared, if I square both sides, is equal to 1 minus x squared. If I add the x squared, I get 1. But it's just the top half of the circle because it's not y is equal to plus or minus. And knowing what this one looks like is a line going down starting at 1, I realize that 1 is all I need to really reach on this one. So planning out your graph ahead will help you make a nice big graph. So my circle, I've already kind of determined is in black. So leave that in black. And then I'll do this one in blue. And it goes down like this. So the area that I'm looking at is this, but I'm going to revolve that around the x-axis, which means the black one is going to go like this, and the blue one like this. So when you're looking at this from the side, I know it looks like Pac-Man, but not really, because when it actually is revolving, when this part of the graph comes down around, all you are going to see is this. You're not going to be able to see that cutout. When this entire piece comes down towards you and then goes all the way around, you're actually going to see this solid. Think about it. Where would you have to stand in order to see that this has been cut out like this? You'd have to stand here. You'd have to walk around and look at it from the negative side of the x-axis. And then you would see that it is missing a cone. Actually, I'll make it dotted just so you can see it. It's not actually there. It's just like this. Okay, so that piece is missing. So I'm going to run it. I'm going to run it through my slicer, and what shape does that make? So here's my slice, but it's missing this. So if you ran it through your slicer, it is missing this inner piece. So my volume is going to be the sum of all these washer shapes, pi r squared minus pi little r squared. Which one is creating the outer washer and which one is creating the inner washer? The outer washer is being created by the half circle, square root of 1 minus x squared, and the inner washer is being created by the line, 1 minus x. I'm going to start my slicer at 0, and I'm going to keep slicing until I get to 1. All right. This is really just practicing integration, which I will quickly do, but again, you should really be able to do this on your own. So when you square root, you get 1 minus x squared minus, be careful here, I pulled the pi out. This is 1 minus 2x plus x squared, but then don't forget to distribute this negative, which is minus 1 plus 2x minus x squared. So now the 1's are going to cancel, and this is just going to be 2x minus 2x squared dx. So that's what you're actually going to integrate. The volume is pi times 2x squared over 2, just becomes x squared, minus 2x cubed over 3 from 0 to 1. I plug in the 1, and I get 1 minus 2/3 minus, when I plug in the 0, I do get 0, but not every time. Don't get too comfortable with that. And of course, 1 minus 2/3 is 1/3. So 1/3 pi, which is the answer, or pi thirds, same thing. Number 4. Find the volume of the solid formed by revolving the region bounded by the graphs of y is equal to x squared plus 1, so an upward parabola that's been moved up 1, y is equal to 0, x is equal to 0, and y is equal to 1 about the y-axis. So this is our first one that's a little bit different. And I can see, though, that I don't need very much of this graph, so I'm just going to make it this big. And actually, if it's going around the y-axis, I won't need this at all. So y is equal to x squared plus 1. So from here, up 1, and then over 2, and up 4. But I don't really need to get those points because I saw that it ended at 1. So at x is equal to 1, it's right there. And at x is equal to 0, that's right here. And y is equal to 0 is right here. So they've really marked off a very specific region, which is this one. And now they want that to go around the y-axis. So what shape is that going to make? As this line comes around, what are you going to see? You're actually just going to see a cylinder. It's going to look just like that. Where would you have to stand to understand what this does to it? You would have to stand up top of it. You would have to be able to see that it's missing, if you were to look in from the top, it's missing a bowl-shaped section like that. So a little bit hard to visualize, but it is the most important part. So make sure that you kind of take a minute and wrap your head around that. So I'm going to run this through a different slicer now. I'm going to start at the bottom here, and I'm going to start making my slices. Slice. What shape is that? Those are just discs. And they're all identical discs. They're all discs. So I can just go all the way from 0 to 1 and just be making discs. This x squared plus 1 has nothing to do with the problem at this point. It's just going to be pi r squared. And what is the radius every single time? It's just 1. And then I'm going to do this next part, and this is going to make a washer. When I'm up here, there's going to be that outer radius minus that inner radius. It's definitely making a washer from 0 or from 1 to 2. It's making washers. What is the outer one? So pi r squared minus pi r squared. What is the outer formula? Well, remember, you're always just trying to think about what the radius is. The radius from here to here, every single washer is still just 1. But if you wanted to think it in terms of the function minus the function, then remember, since we're going around the y-axis, everything is backwards. So this function is x is equal to 1. And then this one, which we normally think of as y is equal to x squared plus 1, we need to get it in terms of x is equal to. So this one's x is equal to 1. And this one is y minus 1 is equal to x squared. X is equal to plus or minus, but we only want the plus, y minus 1. And this one is going to create my inner radius. So the square root of y minus 1. And then since we're going around the y-axis, we do want to write dy, which I need to change this one to dy also. I had a dx there. Sorry about that. All right, so let's actually do this integration. This is feeling a little cluttered to me, so if you don't mind, I'm just going to erase this to make room for my actual integration. So when I integrate just pi times 1, which is just pi, I just get pi y from 0 to 1, which is just pi. So that is the entire volume of this cylindrical shape, this cylinder, volume of the cylinder that's underneath my bowl shape. So there's part of it, remember, that's completely solid. And of course that should make sense because the volume of a cylinder is pi r squared h, and since the radius is 1 and the height is 1, it is just pi. So you could have done that using geometry. You didn't actually have to use calculus, but people kind of get into that mode, so I wanted to make sure you understood it. All right, this one, let's simplify this a little bit. Let's take the pi out to make our life easier. And this is just 1 minus. When you square a square root, of course, you just get y minus 1. But this negative needs to be distributed. So it's minus the y minus 1, which is going to make this minus y plus 1 dy, which is going to be pi from 1 to 2 of 2 minus y dy, which is pi times 2y minus y squared over 2 from 1 to 2, not a 0 this time. And when I plug this in, we're going to add this to our pi over here. I don't want you to lose sight of it. When I plug a 2 in, I get 4 minus 2. When I plug in a 1, I get 1 minus 1/2. Not 1, sorry, 2 minus 1/2. So that's 4 minus 2, but then minus 2 again, all ends up canceling, and you just get the plus 1/2. So plus pi halves. Pi halves plus pi is 3 pi halves. I know some of you just plugged it into your calculator and got it that way. but 3 pi halves is our answer. Last one. The region in the first quadrant enclosed by the y-axis and the graphs of y is equal to cosine of x and sine of x is revolved around the x-axis to form a solid. So you can draw this better if you know where they're going to intersect. So sine, of course, starts at 0, goes up to 1, and then goes back down to 0 and keeps going. This is pi, and this is pi halves. Cosine starts at 1 and goes down to pi halves, like this. And where is that point of intersection? That point of intersection happens at pi fourths, comma the square root of 2 over 2. So this is the region that we're going to rotate right here. We could find its area really easy just by doing the top minus the bottom. But when we're doing volume, we're going to be flipping it around. So let's see. I'm going to make a 1 there and do the same thing. And for my sine. Okay. So what shape is it? Well, we're in the washer section, so you already kind of knew it was going to be washers. But how does it look to you? What shape do you see? So hopefully you see that cosine is coming down, but then because it gets cut off, it's perfectly flat. I like to think of it like a dog dish. I mean, on its side, but it's like a dog dish because then it has an interior, although I don't think a real dog dish would, like a real dog dish would just like look like that from there. But ours is going to, I'm going to make it dotted because it doesn't actually, you can't see it from the side. Okay, but it looks something like that. So these washers are all going to look like that every single time. So my volume is pi r squared outer radius, this one, which in this case is being created by the sine or the cosine. Look carefully. If you have to, just make one of them. So you could just make one of them kind of dark, like this, and then this. What's creating that outer radius on that? It's definitely the cosine graph. So cosine of x minus sine of x. So probably by now you've gotten the hang of this. The question is, how do you integrate this? You could do it on your calculator, which is not too terrible. Make sure your calculator's in radians and the point of intersection, your slicer is going to go from 0 all the way up to pi fourths. But what if you had to do it by hand? Well, unfortunately, if you had to do it by hand, it would be really annoying if you didn't remember that cosine squared minus sine squared is actually just cosine of 2x. And then it's not too bad at all. So a little identity from pre-calculus. Dx, and then you can use u substitution to finish that up. The final answer is pi halves. All right, that's it for volume by washers. Have a great day.